Should we do some actual math? So I said that we were going to talk about percentages today, and I kind of want to talk through a little bit of vocabulary here. These are probably mechanics that you already know, but I don't want to take that for granted, just like vocabulary wise. So if I said something like, where are we at? 11, 12, 16. Sorry, I'm trying to do real math. If I said that 65% of our class joined on Zoom today. There are 5 students in the classroom. How many students are on Zoom? Okay, I made up these numbers because actually the fraction is a little bit messy and I didn't want to deal with the messiness. So I made this 65%. We are going to actually attack this problem, even though the numbers don't quite match up with reality today. But when we say 65%, that percent symbol, this thing right here, which we read as percent, for any Latin root lovers or Spanish speakers, it is por cien, like it's 65 out of 100, right? But this means mathematically 65 divided by 100, or we can write it as a decimal as 0.65. So when we write the percentage symbol, it's convenient notation. It's notation that we see a lot. We see it in newspaper articles. We see it in advertisement signs. But it actually, this notation means 65 out of 100, or as a decimal, 0.65. So if I add 5%, that means 5 out of 100, or 0.05. So this thing is just notation. It's kind of a mathematical symbol, but it's really more of a mathematical placeholder for what it really is. That word of in a statement, like if I say 65% of, that of means I'm going to multiply something. So if I were translating this into that first sentence into mathematical symbols, I could write that as that 65% of our class joined on Zoom today. I could say 65 out of 100 times our class size equals the Zoom students. Now, one of the other things to note when we're talking about percentages is if I want to capture all of the students in class, then that's 100%. When we talk about all of something, that's 100 out of 100, or 1, or 100% in terms of notation. So if I wanted to kind of get at this question, I know that 65% of our class size is what's going to tell me how many Zoom students are in the room. but I didn't actually give us enough information to come up with class size. And remember, I'm faking it. So if you're on Zoom and you think you can cheat by just looking at how many participants there are, I made up the 65%. Sorry. So we got to actually work through the math. So what I do know is that there are 5 students in the classroom. I didn't make that part up. And if the entire class is represented by 100%, but 65% are on Zoom, then I know that those 5 students represent the remaining percentage. So I'm looking at 35% is that remaining percentage. I throw my pencil. So 35 out of 100 times the class size is going to equal the 5 students in the room. Oftentimes when I'm doing word problems, I know that the textbook is going to suggest that you replace things with variables. It is certainly faster to replace things with variables as long as you remember what those variables are. So by default in math problems, we usually choose X and Y, but I recommend choosing variables that are going to help you remember what they stood for. So pick whatever letter makes sense to you. Here, the thing that we're trying to figure out is class size. So I'm going to replace that with a C. So 35 over 100 times C is equal to the 5 students in the room. Some of you may have already done this math already. I don't know, but if I wanted to solve for C here, kind of using what we were working on Wednesday, I would look at this problem and say, oh, I have fractions. Let's get rid of those fractions. I'm going to choose to multiply both sides by 100. Which is going to leave me with, on the left-hand side, I'll have 35C, and 5 times 100, I'm actually going to leave as 5 times 100. The reason is that I'm kind of looking ahead and realizing that I'm about to divide both sides by 35 to get the C by itself. And if I have to reduce that fraction, then I actually want this to say 5 times 100 so that I'm going to be able to rewrite that 35 and cancel a 5 out. So if I divide both sides by 35, but I write over here, it's my 1, but over here, I think about that as 5 times 100 and then 35 as being 5 times 7. Then the 5 over 5 cancels out. And I would get that our class size is 100 divided by 7. Now, obviously, that is not a pretty number, which is why I said I just made the problem up, because I was trying to do math in my head with the actual numbers and I couldn't do it in my head. But what is 100 divided by 7? Here's the place where I pull out the calculator. You all can't read that. On the calculator, and no, I do not expect anyone doing long division. 100 divided by 7 is not worth your time. Don't pull out long division on me. Just pull out the calculator. That's about 14.3. Now, obviously, I don't even want, we do not have a 30% of a human in the class, right? Like unless someone, I don't know, brought their dog, it's about 30% of the weight of a human or something. I don't want to contemplate that. In real life, these numbers don't really work, but as a working through a percentage problem, it was just fine. By the way, there are 11 students on Zoom, 5 in the room. There are actually 16 students in the class. I didn't get too bad on my estimate. That was kind of a lot all thrown into one problem. Questions? I'm checking the Zoom chat too. So. Yeah.
So just to be sure, the 35% comes from what's missing from the 65, right? To make that good.
Totally. So we got the 35. I didn't explicitly write that, but we got that 35 out of 100 because like the total would have to be the 65% on Zoom plus some percentage in the room. And since the total was going to be 100%, that missing piece had to be 35%. Other questions before we move on and do more fun things? Okay. Just a couple more kind of percentage practicey things. If I say that I don't know, $30 hat is on sale with a 15% markdown. How much will it cost? Again, my guess is that some of these things you're probably used to doing and maybe even have ways to figure these things out in your head. 15% is not bad. When I have to do 15%, I usually do 10% and half of that. And that's how I would do that in my head. But if we were writing this as a math problem, if it's on sale with a 15% markdown, then we have two options. I can either think about, so what's the discount? And subtract that from 30, or how much do I still have to pay? So if I go from the standpoint, and we should get the same answer either way, but if I go from the standpoint of how much is the discount, then 15% of $30, that of says I'm going to multiply. So 15%, I can think about that as 15 over 100 times that $30. And I'm going to put the 30 up here on top. If it helps you, you can write that as 30 over 1. Now, if we want to do this without reaching for the calculator, then you could multiply 15 times 30 on top. Or we can make the fractions smaller first. I usually vote smaller first, personally. So I'm going to look at that as 15 times 3 times 10, taking that 30 and thinking about it as a 3 times 10, and the bottom is 10 times 10. So that I've got a 1 over here. And then the 15 and the 10, those can both be broken down as 5 times 3 for that 15 and 5 times 2 for the 10. Now my 5s are 1 and I've got 9 over 2. Now I'll be honest, if I was standing in the store and trying to figure out how much that hat costs, I'm not thinking about 9 over 2. It's 4.5. Money, I tend to think in decimals instead of fractions. So I think of that 9.2 immediately as 4.5. And if that's how much the discount is, then the answer for how much I'm going to pay is the original $30 minus that $4.50 discount. And I think I mentioned this on Monday, but if I have to do that subtraction in my head, I am not lining numbers up and borrowing tens from things. I'm going to subtract 5 and then add 50 cents back in. So 30 minus 5 would take me to would take me to $25, and then I'm adding the 50 cents back in. good times. Now, the other way to think about this is more similar to how I did the problem with the students in the classroom, which is instead of thinking about the discount, I can think about, so what percentage do I have to pay? If there's a 15% discount, then of the 100% I had to pay, if I take that 15% discount, we're down to 85%. So this one I can think about as what is 85% of the $30, or 85 over 100 times 30. I'm never going to do this in my head. This is never the choice I'm going to make. It is definitely not the choice I'm going to make if I'm like actually standing in a store trying to do this. Let's be real. If I'm standing in the store trying to do this, I'm pulling out my calculator. Yeah. But I'm not going to choose to do this because I don't really know what 85 is divisible by. I mean, like, I know it's divisible by 5, but that is not a multiplication fact that I just have off the top of my head. This is definitely the choice I'm going to make, but let's fight through it like we have to. Like, let's pretend we have to fight through this. So I know 85 is 5 times something. And I know that the 100 is 5 times 2 times 10, and that 30 is 3 times 10. And that's my only missing piece. And I just realized my computer's making little noises. So let me turn my little computery noises off. That's kind of annoying. Probably not annoying to you, only annoying to me. Computery noises off. Cool. So if I have to figure out how many times or what times 5 is equal to 85, I probably am stuck with the division algorithm personally. And I'm going 5 times what is going to get me close to 8 without going over? Well, that's a 1. I multiply the 5 times the 1. I've got a 5. 8 minus 5 is 3. And then I bring the 5 down. 5 times 7 is 35. There we go, 17. We will spend more time on division in a different chapter. But now I can grab my 1 or my 10s, which turn into a 1, and my 5s, which turn into a 1. But look, now I'm back to having to do 3 times 17 and then dividing that by 2. There is nothing nice about doing the math this way. 3 times 17. 51 over 2. And then I'm still left with 51 over 2. I still don't know how much that is. Okay, but 50 over 2 would be 25. And then I'd still have the 1 over 2. Okay, I can get to 2550. Now, why did I fight through this? One, because it's good practice with fractions and stuff, but more fundamentally, there is almost always more than one path to the correct answer in a math problem. And it doesn't matter which way you fight through something unless you're under a time constraint. So one of the things that I just want floating in the back of your head working through any problem this quarter is to be recognizing patterns of sort of what is the most efficient way through something. And if your multiplication facts are super solid, then maybe this is the efficient way for you to get through the problem. For me, this was definitely the efficient way. And there are going to be lots of cases throughout this quarter where really we're just practicing multiple ways to approach the same problem so that you're adding things to your toolkit. Okay. Yeah. To get from here to here, that very last step.
Yeah, like the 30 minus like the 4.5. Like on the calculator, obviously I can see it from there, but like me trying to do it in my head.
Oh yeah, totally. So let's look at both of the approaches that I took there on just like that last step. So if I have 30 minus 4.5, what I'm doing in my head is I'm taking that 4.5 and I'm actually thinking about that as saying minus 5 plus 0.5. Because if I subtract 5 and then I add 0.5 back, this is the same as the negative 4.5. And that I can do in my head. So if I had 40 minus 3.6, I look at that 3.6 and I think about that as 40 minus 4 plus 0.4. To get back to 3.6.
Oh, okay.
Yeah. Or if I had 50 minus 7.2, I'm going to think about that negative 7.2 as negative 8 plus 0.8. Now, when I did the other way with the, like this last step, kind of how I thought about those fractions. That up. So how I thought about those fractions and the 51 over 2, I thought about this one as 50 plus 1 over 2, because that I can break apart like this. And 50 over 2, I know that's 25. And a half I can write as 0.5. You don't have to be good at dealing with the numbers in your head. It just helps in terms of speed getting through a problem if you don't have a calculator. But in terms of this class, I don't mind at all if you're using a calculator on homework or the quizzes, right? It's a good thing to practice to move away from, but I don't want it to mean that you can't get through the problem because the numbers are stopping you. Okay. Like I printed stuff out somewhere. So section 2.6 of our textbook has a whole bunch of word problems. I just wanted to like briefly talk about reality. No one cares how old Shelley and Michelle are. No one cares how old Carrie and Dan are. No one's solving world problems by doing these things. No one cares if Marissa has 440 in quarters and dimes. Like, this is all the point of it is just to practice translating words to math. So if it feels pointless and it feels like these are some real dumb real world problems, they are really dumb real world problems. We're just practicing translating things to math. But if you're thinking about all of the types of word problems that this textbook gives us, the truth is the ones that are going to show up the most in calculus are the stuff that have to do with geometry or chemistry. So if we're talking about like ratios of alcohol mixtures or something, that's something that could show up, and the geometry stuff shows up. And some of the problems that are just talking about numbers. So I want to go through just a few of these. So I'm picking some of the like numbery problems from 2.6 just to practice translating words to math symbols. So if you want to play along, I'm in section 2.6. And I'm looking at the problem set at the end. And I guess I should make that actually show up on the screen. So the first one on here says the sum of a number and 5 is 13. So if I'm translating this into mathy symbols, sum means I'm going to be adding stuff. Anytime we see a number, that we should probably pick a letter to replace that with. I like n because it's a number. X is totally fine, but I like n because it says number. So I'm going to replace this with n. Since I have the sum of n and 5, that and 5 thing, because it was a sum, means I'm going to be adding 5. The word is tells me to write an equal sign, and there's my 13. So n plus 5 is equal to 13, which must mean n is equal to one number is 3 less than another. Their sum is 15. Find the numbers. Well, one number is 3 less than another. So I've got this number thing. I need to pick a letter. I'm going to pick n because it's a number. But I have another number. So I'm going to pick m because it's next to n in the alphabet. I don't know. You can pick X and Y, A and B. Doesn't matter. That choice is arbitrary. But one number is 3 less than another number is tells me I'm going to write an equal sign. So n is 3 less than m. And I know we talked about this, I don't know, maybe like last Friday or something, but the order matters here. So 3 less than, that less than means we're subtracting 3. So this is going to say that n is equal to m minus 3. If their sum is 15, sum is telling me to add them. So n plus m equals 15. So you've got choices of how to deal with this, right? Technically, this is two equations with two unknowns. I choose to think about this as saying, well, if n is equal to m minus 3, and it's the same n in the entire problem, then I'm just going to take this and replace the n down here. So I'd have m minus 3 plus that m is equal to 15. Moving stuff around, that's 2 m's over here. And if I add 3 to both sides, I'll get 18, which means m is equal to 9. Now I haven't actually, I haven't actually finished answering the question because the question asked me to find the numbers plural. So I figured out that m is equal to 9, but I also need to give the value of n. And it doesn't matter which of these equations we think about. I'm going to put it into the top one because it already says n equals. So n would be 9 minus 3 or 6. Let's skip a bunch of those, but I'm going to pause for a second in case anybody had questions. Let's talk through some geometry formulas. At some point in time in a previous life, you probably have seen all of these geometry formulas before. With any luck, you even remember some of them. But I'm here to tell you that everything I'm about to list, you're going to have to remember all of them. You're going to need all of these in calculus. You're going to need a bunch of them in here. But the list of what you actually need to memorize isn't that long. So let's start off with a rectangle. Fun facts about rectangles. All of the interior angles are 90 degrees. And we usually denote that with a little box to show that it's 90 degrees. We're not going to do too much geometry here. Size of the rectangle, depending on the problem, might be called the length and the width, or in another problem, they might be the base and the height. Doesn't matter at all whether you call them length and width or base and height. Our textbook tends to use length and width, so that's what I'm going with. It doesn't matter which side you label as the length and which side you label as the width. So I'm just going to call that the length and not the width. So a couple of formulas that we're going to need. We're going to need a formula for the perimeter. And a formula for the area. So for the perimeter of the rectangle, that's just the distance around the outside of it. Well, one thing to note about a rectangle is that the sides, parallel sides, have the same length. So if this is W, the length of this side is also W. And if that side is L, then the length of this side is also L. So getting at that perimeter, that's a W plus an L plus another W plus another L. If I like walked all the way around it. So that's 2W plus 2L. The area of a rectangle is length times width or base times height. I'm going to write that in words. Length times width or L times W. We're also going to work with triangles, and there are different vocabulary words that we can associate with triangles. no matter what the shape of the triangle is, and I'm trying to make this not look particularly regular in any way, but no matter what the shape of a triangle is, the height and the base are what give me the area. So for any triangle, the area is equal to 1/2 the base times the height. But we also have some formulas particular to specific types of triangles. And I would say that for now, the one that it's important to know, just because it shows up a lot, is when we have a right triangle, magic of erasable pens. For a right triangle, which means one angle is 90 degrees. For a right triangle, the same thing stands. That area is still 1/2 base times height. But there's also a particular relationship with the sides of a right triangle. We often label these as A, B, and C. And A squared plus B squared is equal to C squared. Now, the one thing that's important when we label a right triangle this way, and specifically when we're using this formula, C has to always be that diagonal piece that is not touching the corner that has a 90-degree angle. And so this side, that longest side, has a special name. So C is that longest side, and it's called the hypotenuse. One other thing that it is that will come up for triangles, and I guess I'll draw another triangle, why not? For any triangle, the sum of the interior angles is equal to 180 degrees. And we often use Greek letters when we talk about the angles. So I'm going to call these alpha, beta, and gamma. I'll write it out in words. The sum of the interior angles equals 180 degrees, or alpha plus beta plus gamma would equal, 180 degrees. One last set of geometry formulas in terms of pictures and fun shapes. We should talk circles. Slide this up just a little bit. So when we're talking about circles, circles are defined really by where the center is and what the radius is. So the radius is measured from the center of the circle out to any edge, and the perimeter gets a special name for circles. And instead of using the word perimeter, we use circumference. They mean the same thing. It's the distance around the edge. We just give it a special name when we're talking about circles. And that circumference is equal to 2 times pi times the radius. And the area for a circle is equal to pi times the radius squared. If you haven't, well, no, you've encountered our friend pi before. You don't need to like memorize millions of digits, although lots of people get really into that. The internet has lots of videos, but knowing that pi is about 3.14 is good. Just kind of keeping that one in your head, that pi is, I put an equal sign. I should not. I should have used the squiggly equal to mean not quite equal to 3.14, approximately equal to 3.14. One more word that we talk about with circles is diameter. And so if I measured the longest distance from edge to edge on the circle, we call that a diameter. And that diameter is equal to twice the radius. That's really all I got in terms of geometry formulas that I think you ought to know for two-dimensional shapes. We don't need anything with three-dimensional shapes just yet. So this is it. But let's do a word problem where we have to use some of these geometry formulas. So I'm still in that same problem set. So let's have some fun. And oh. The length of a rectangle is 6 feet more than 3 times the width. The perimeter is 36 feet. Find the length and width. By the way, just another phrase that comes up. So this happens to say find the length and the width, but this could have also said find the dimensions. And when we talk about the dimensions of a rectangle, we should always report out both the length and the width. Do you all want a minute to do y'all want to do this on your own? You want to watch me do it? It's Friday. I see not a ton of writing going on. I'm gonna just do it. So the length of a rectangle is 6 feet more than 3 times the width. Well, if I start dissecting that, length is, okay, L equals 6 feet more than, so I know I'm gonna be doing something plus 6. And then I've got 3 times the width. 3 times the width. The perimeter is 36 feet. So our perimeter is equal to 36 feet, which is fine, but more useful to know that formula for the perimeter that includes the length and the width. So those 36 feet, that's twice the length plus twice the width. Technically, that's 2 equations and 2 unknowns. But if I know that L is equal to 3W plus 6, then I can pop that 3W plus 6 right in here for L. So out of 36 is equal to 2 times 3W plus 6 plus 2W. No fractions, but we do still have to worry about the order of operations. I'm looking at parentheses here. The invisible operator between the 2 and the parentheses is multiplication. And I do have addition inside of the parentheses, meaning it's somewhere that we're going to have to distribute to. So I'm going to have to take that 2 and distribute to the 3W and also distribute to the 6. Since my W's are already on the right-hand side, I am going to leave them there. 6W plus 2W is 8W, and I'm going to subtract 12 from both sides. So I've got 24 is equal to 8W. And if I divide by 8, W must be equal to 3. Since we were asked to find both the length and the width, I've got a width, but I need a length. So I'm going to go back to the thing that says L equals, and that's 3 times my width plus 6. 3 times 3, 9. 9 plus 6 is 15. And then I am going to be careful to include units. The units in this problem are given in feet. So I'm going to make sure that I report that the width is 3 feet and the length is 15 feet.